Installing surge suppressors on each load center may provide benefits in a 400 amp 2 load center service. Improved surge protection is one benefit. Each suppressor provides an additional layer of protection for the corresponding load center and its connected devices. By having two suppressors, the risk of damage caused by lightning strikes or power surges is reduced. Reduced voltage drop is another benefit. Suppressors can help reduce voltage drop by ensuring that surges are diverted to ground rather than passing through the electrical system. This can improve the overall efficiency and performance of the electrical equipment. Redundancy is also important. If one suppressor fails, the other can still provide protection for the load center it serves. This redundancy enhances the reliability and longevity of the surge protection system. Consider some technical considerations. The effectiveness of a surge suppressor relies heavily on its proper grounding. Ensure that both suppressors are properly connected to a dedicated grounding rod or grid. Surge capacity is also important. Consider the surge capacity of the suppressors when selecting units. The capacity should be sufficient to handle the potential surge currents in the electrical system. Metal oxide varistor ratings are critical. The metal oxide varistors within the suppressors determine their ability to absorb and dissipate surge currents. Higher metal oxide varistor ratings provide increased surge protection. Some manufacturers recommend installing a surge suppressor on each load center in a multi-load center system. For example, one manufacturer recommends using two surge protectors in a 400 amp service, one for the main load center and one for the sub-load center. This approach is supported by their testing and research. Based on the benefits and technical considerations, it is generally recommended to install a whole house surge suppressor on each load center in a 400 amp 2 load center service. While the second suppressor may provide marginal additional protection, it enhances the overall reliability and effectiveness of the surge protection system. Key considerations when selecting and installing surge protection devices include firstly, the type of surge protection device, or SPD, secondly, its suitability for the application, and thirdly, correct installation practices. There are three main types of surge protective devices: firstly, Type 1, secondly, Type 2, and thirdly, Type 3. Type 1 surge protective devices are installed on the line side of the main overcurrent protective device in the service entrance. They are designed to protect against external surges such as lightning strikes. Type 2 surge protective devices are installed on the load side of the main overcurrent protective device, typically at distribution panels or subpanels. They protect against surges generated within the facility, such as those caused by switching inductive loads. Type 3 surge protective devices are installed near sensitive equipment, such as computers or electronics. They provide localized protection against residual surges that may have passed through the Type 1 and Type 2 SPD. The selection of a suitable SPD depends on several factors, including firstly, the voltage and current rating of the electrical system, secondly, the expected surge current, and thirdly, the level of protection required. The voltage rating of the SPD must match the voltage of the electrical system. For example, in a 120/240 volt single-phase system, the SPD should have a voltage rating of at least 150 volts to ground. The surge current rating of the SPD indicates its ability to withstand high current surges. The surge current rating should be greater than the expected surge current in the electrical system. The level of protection required depends on the sensitivity of the equipment being protected. Sensitive equipment, such as computers and electronics, requires a higher level of protection than less sensitive equipment, such as lighting fixtures. Correct installation practices are essential for ensuring the effective operation of SPD. The following are some key installation considerations: firstly, grounding, secondly, lead length, and thirdly, overcurrent protection. SPD must be properly grounded to provide a low impedance path for surge currents. The grounding conductor should be as short and straight as possible. The length of the conductors connecting the SPD to the electrical system should be minimized to reduce impedance. The conductor should be no longer than recommended by the manufacturer. SPD should be protected by an overcurrent protective device, such as a circuit breaker or fuse. The overcurrent protective device should be sized to protect the SPD from overload currents. Additional information on surge protection can be found in the National Electrical Code, or NEC. Article 242 covers surge protection devices. It provides requirements for the selection, installation, and protection of SPD. Some key sections of Article 242 include 242.4, which covers the rating of surge protection devices. 242.8 covers the installation of surge protection devices. And 242.12 covers the connection of surge protection devices. There are several types of surge protection devices. Firstly, metal oxide varistors, secondly, silicon avalanche diodes, and thirdly, gas discharge tubes. Metal oxide varistors are the most common type of SPD. They are made of a semiconductor material that changes resistance with voltage. When a surge occurs, the resistance of the metal oxide varistor decreases, allowing the surge current to flow to ground. Silicon avalanche diodes are similar to metal oxide varistors, but they have a faster response time. They are typically used in Type 3 SPD to protect sensitive equipment. Gas discharge tubes are filled with a gas that ionizes when a surge occurs. The ionized gas provides a low impedance path for the surge current to flow to ground. Gas discharge tubes are typically used in Type 1 SPD to protect against lightning strikes. When selecting an SPD, it is important to consider the following factors. Firstly, the voltage and current rating of the electrical system. Secondly, the expected surge current. Thirdly, the level of protection required. And fourthly, the type of surge protection device. The voltage rating of the SPD must match the voltage of the electrical system. For example, in a 120/240 volt single-phase system, the SPD should have a voltage rating of at least 150 volts to ground. The surge current rating of the SPD indicates its ability to withstand high current surges. The surge current rating should be greater than the expected surge current in the electrical system. The level of protection required depends on the sensitivity of the equipment being protected. Sensitive equipment, such as computers and electronics, requires a higher level of protection than less sensitive equipment, such as lighting fixtures. SPD are an essential component of any electrical system. They protect against voltage surges that can damage equipment and cause fires. By selecting and installing SPD properly, electrical systems can be protected from the damaging effects of voltage surges. Another consideration is the surge protective device's nominal discharge current rating, also known as IN. This rating indicates the amount of surge current the SPD can withstand 15 times without failure. A higher nominal discharge current rating indicates a more robust SPD. The surge protective device's voltage protection rating, or VPR, is the maximum voltage that the SPD will allow to pass through to the protected equipment during a surge event. A lower voltage protection rating indicates better protection. The surge protective device's short circuit current rating, or SCCR, is the maximum short circuit current that the SPD can withstand without failure. The short circuit current rating should be greater than the available short circuit current at the point of installation. The surge protective device's enclosure type should be suitable for the environment in which it will be installed. For example, an SPD installed outdoors should have an M4 enclosure to protect it from the elements. The surge protective device's status indicator provides information on the SPD operating status. Some SPD have visual indicators such as LED, while others have audible alarms. A surge protective device's warranty provides coverage for defects in materials and workmanship. A longer warranty indicates a more reliable SPD. When installing a surge protective device, it is important to follow the manufacturer's instructions. The SPD should be installed by a qualified electrician. The SPD should be installed as close as possible to the equipment being protected. The SPD should be properly grounded. The conductors connecting the SPD to the electrical system should be as short and straight as possible. The SPD should be protected by an overcurrent protective device. Surge protection is a critical aspect of electrical safety. By understanding the different types of SPD, their ratings, and installation requirements, the damaging effects of voltage surges can be prevented. Surge protection devices are also called transient voltage surge suppressors, or TVSS. A transient voltage surge suppressor is designed to protect electrical and electronic equipment from voltage spikes. Voltage spikes can damage or destroy sensitive electronic components. Transient voltage surge suppressors work by diverting excess voltage to ground. This prevents the voltage spike from reaching the protected equipment. Transient voltage surge suppressors are available in a variety of types and sizes. The type of TVSS needed will depend on the application. Some common types of TVSS include firstly, point-of-use TVSS, secondly, panel mount TVSS, and thirdly, hardwired TVSS. Point-of-use transient voltage surge suppressors are plugged into an electrical outlet. They are used to protect individual pieces of equipment. Panel mount transient voltage surge suppressors are installed in an electrical panel. They are used to protect all of the equipment connected to the panel. Hardwired transient voltage surge suppressors are wired directly into the electrical system. They are used to protect the entire electrical system. When selecting a transient voltage surge suppressor, it is important to consider the following factors. Firstly, the voltage rating. Secondly, the surge current capacity. Thirdly, the clamping voltage. And fourthly, the response time. The voltage rating of the TVSS should be greater than the voltage of the electrical system. The surge current capacity of the TVSS should be greater than the expected surge current. The clamping voltage of the TVSS is the voltage at which the TVSS will start to divert excess voltage to ground. The response time of the TVSS is the time it takes for the TVSS to start diverting excess voltage to ground. The lower the clamping voltage and the faster the response time, the better the protection. Transient voltage surge suppressors should be installed by a qualified electrician. The TVSS should be installed in accordance with the manufacturer's instructions. Transient voltage surge suppressors are an important part of any electrical system. They can protect electrical and electronic equipment from damage caused by voltage spikes. Surge protection is a layered approach. A whole-house surge protector is typically installed at the service entrance to protect against external surges. However, it is important to also use point-of-use surge protectors for sensitive electronics such as computers and televisions. This provides an additional layer of protection against surges that may have passed through the whole-house surge protector. The National Electrical Code, or NEC, provides requirements for the installation of surge protection devices. Article 242 of the NEC covers surge protection devices. This article includes requirements for the location, sizing, and installation of surge protection devices. The NEC also requires that surge protection devices be listed by a qualified testing laboratory. This ensures that the devices meet safety standards. When installing a surge protection device, it is important to follow the manufacturer's instructions and all applicable codes. This will help to ensure that the device is installed correctly and will provide effective protection against surges. Surge protection is an important part of electrical safety. By using surge protectors, electrical equipment and electronics can be protected from damage caused by surges. Another topic to cover is the difference between surge protection and lightning protection. Surge protection is designed to protect against transient voltage surges, which are short-duration voltage spikes that can damage electrical equipment and electronics. Lightning protection is designed to protect against direct lightning strikes, which are much more powerful and destructive than transient voltage surges. Surge protection devices are typically installed at the service entrance of a building to protect against surges entering the building from the power grid. They are also installed at the point of use to protect individual pieces of equipment. Lightning protection systems are typically installed on the roof of a building to intercept lightning strikes and conduct the current safely to ground. Lightning protection systems typically include lightning rods, conductors, and grounding electrodes. Surge protection devices are not designed to protect against direct lightning strikes. If a building is struck by lightning, the surge protection devices may be damaged or destroyed. However, a lightning protection system can help to protect the building and its contents from the destructive effects of a direct lightning strike. In summary, surge protection is designed to protect against transient voltage surges, while lightning protection is designed to protect against direct lightning strikes. Both types of protection are important for electrical safety. When considering surge protection for a 400 amp service with 2 load centers, it's also relevant to understand the concept of cascading surge protection. Cascading surge protection involves installing surge protective devices at multiple points in the electrical system, starting at the service entrance and continuing down to individual circuits or equipment. This approach provides a more comprehensive level of protection than relying on a single surge protective device at the service entrance. The surge protective device at the service entrance, typically a Type 1 or Type 2 device, handles the initial surge current from external sources like lightning or utility switching. Downstream Type 2 or Type 3 surge protective devices provide additional protection for sensitive equipment by clamping down on any residual surge energy that may have passed through the upstream device. This cascading effect helps to reduce the surge voltage to a safe level for sensitive electronics. When selecting surge protective devices for a cascading system, it's important to coordinate their voltage protection ratings. The downstream devices should have a lower voltage protection rating than the upstream devices to ensure that they clamp down on any remaining surge energy. It's also important to consider the surge current capacity of each device. The upstream devices should have a higher surge current capacity than the downstream devices to handle the initial surge current. In a 400 amp service with 2 load centers, a cascading surge protection system might involve installing a Type 1 or Type 2 surge protective device at each load center, followed by Type 3 surge protective devices at the point of use for sensitive equipment. This approach provides a robust and comprehensive level of surge protection for the entire electrical system. Consider the impact of harmonics on surge protection. Harmonics are unwanted voltage and current distortions that can be present in electrical systems. They can be caused by nonlinear loads such as electronic devices, variable frequency drives, and arc furnaces. Harmonics can have a number of negative effects on electrical equipment, including firstly, overheating, secondly, increased energy consumption, and thirdly, premature failure. Harmonics can also interfere with the operation of surge protection devices. Surge protection devices are designed to protect against transient voltage surges, which are short-duration voltage spikes. Harmonics, on the other hand, are continuous voltage and current distortions. Harmonics can cause surge protection devices to operate prematurely or to fail altogether. To mitigate the impact of harmonics on surge protection, it is important to firstly reduce the level of harmonics in the electrical system, and secondly, use surge protection devices that are designed to withstand harmonics. Harmonics can be reduced by using harmonic filters, which are devices that block or reduce the level of harmonics in the electrical system. Surge protection devices that are designed to withstand harmonics typically have a higher surge current capacity and a lower clamping voltage. They may also have additional features such as harmonic filters or metal oxide varistor failure indicators. When selecting surge protection devices for an electrical system with harmonics, it is important to consult with a qualified electrician or electrical engineer. They can help to determine the level of harmonics in the electrical system and to select the appropriate surge protection devices. Another important aspect of surge protection is the concept of let-through voltage. Let-through voltage is the voltage that a surge protective device allows to pass through to the protected equipment during a surge event. A lower let-through voltage indicates better protection. Surge protective devices with a lower let-through voltage will clamp down on the surge voltage more effectively, reducing the amount of energy that reaches the protected equipment. The let-through voltage of a surge protective device is typically specified in volts. It is important to select a surge protective device with a let-through voltage that is appropriate for the sensitivity of the equipment being protected. Sensitive equipment, such as computers and electronics, requires a surge protective device with a lower let-through voltage than less sensitive equipment, such as lighting fixtures. The let-through voltage of a surge protected device can be affected by a number of factors, including firstly, the surge current, secondly, the voltage, and thirdly, the temperature. As the surge current increases, the let-through voltage will typically increase. As the voltage increases, the let-through voltage will typically increase. As the temperature increases, the let-through voltage may increase or decrease depending on the type of surge protective device. When selecting a surge protective device, it is important to consider the let-through voltage rating. A surge protective device with a lower let-through voltage will provide better protection for sensitive equipment. It is also important to consider the other factors that can affect the let-through voltage, such as the surge current, the voltage, and the temperature. The Institute of Electrical and Electronics Engineers, or IEE, provides standards for surge protection devices. IEE Standard C62.41 defines the environment and surge voltages and currents. IEE Standard C62.41 provides recommended practices for surge voltage protection of low-voltage alternating current power circuits. IEE Standard C62.45 provides guidelines for surge testing of equipment connected to low-voltage power circuits. These standards provide guidance for the selection, installation, and testing of surge protection devices. It is important to follow these standards to ensure that surge protection devices are installed correctly and will provide effective protection against surges. The Underwriters Laboratories, or UL, also provide standards for surge protection devices. UL Standard 1449 covers surge protective devices. This standard includes requirements for the safety and performance of surge protective devices. UL-listed surge protection devices have been tested and certified to meet the requirements of UL 1449. It is important to use UL-listed surge protection devices to ensure that they are safe and will perform as intended.